essentially you have the elementary symmetric functions of the roots of this EA whose multiplicity is greater than 0. So this way comes the elementary symmetric function. So for example, assume that there is this x. So a0 is equal to 0, then there is a1, a2, a3, this is delta s, and the word is 2, 1, 0, 2, then you see there is z squared, right? Because there is a 2 here. 1 minus a1 power 1, because there is the 1 here. There is no term, or there is no term in the sense there is 1 here, because this is power 0. Something like it's not there. And then there is 1 minus a1 power 2. Sorry, no, I did a mistake. 1, 2, and 3. Okay? Here you should, here you see, here there is a1, here there should be a 2, and I made a typo. And here there should be the 3. Look at the colors. Okay, the colors tell the truth. Am I clear? There was a typo. This should be a 2 and this should be a 3. So anyway, if you develop it, you see, this is the degree 1 symmetric function on the roots of this. This is the degree 2 symmetric functions on these AIs, and keep going like that. Okay, so note that sigma 0, sigma 1, sigma 2, and keep going like that are the elementary symmetric function of the inverses, to tell the truth, but it's the same as the multisex x ordered increases order of their degree. And obviously, x is identified by sigma x and vice versa. And the degree of sigma x is nothing but the L1 weight of x, the cardinality of the multisex x, and the degree of the support of x is nothing but the Hamming weight. Okay, now, these are sigma codes. You define x and c depends on g and sigma, where g and sigma are, g is in a polynomial here, and such that is co-prime with sigma of all the index set. So all the entropy such that sigma x is equal to a certain constant polynomial up to a constant number, mod g of z for some constant, not zero constant. Okay? Well, these are, you can prove that these can correct asymmetric errors in a very general sense. In the sense that they can correct t minus negative error. As soon as I received a word so that the number of negative errors is below t minus and the number of positive errors is below t plus, I can correct the errors. Okay? So t minus can be 2, t plus can be 100, for example. Okay? And it is up to me to choose, given the same code, what are these parameters. I can use this same code to do many kind of decodings. And this is based on solving this very general key equation that you can see it holds, because this is nothing but the sigma of x, of x union, with the union means the maximum component-wise, y. And it can be decomposed in these two ways, given the definition of the sigma polynomial. To prove this is straightforward. It depends that exponents add up, you know. Okay, now when d is less than or equal to p, p is a prime, these and z and g is z power d, as we are used to, you know, BCH codes, mod z power d, right? And here there is, the sigma here is a 1. What I'm saying is that sigma 0 obviously is 1. Sigma 1 is 0, sigma 2 is 0, and keep going like that. Maybe sigma p may be anything, but then sigma plus 1 is 0 up to wherever is d here. Then I'm telling you this is a linear and Mari BCH code Oh, and when M is equal to P, it is with the Newton identity, you can prove this is a linear Emari Piari BCH codes eventually shorter. Okay? So these are so easy to encode and decode. Decode with this. Here, starting from now, here I'm telling you, I generalize. It seems that times run out so fast, you know. So I'm just telling you the result. But anyway, here, if you generalize this and you put these things, so C, instead of being a number, it's a polynomial power n. How much do you have?
You have 10 minutes.
10 minutes. One. There was an incomprehension. We used two different codes, but now I realized. I told him to do this for 10 minutes, not for 1 minute. So don't see.
One question.
Okay, now I can be a little bit, but not much analyzed. So the hypothesis is the same. G is Z power D. Then if you assign the same code, the code becomes like this, right? Then all the relation of all the distances are this. The symmetric distance is greater than the lead distance of this code. The minimum lead distance of it is greater than D. This D. And this makes it, this is the BCH bound in this case, you see? And also the symmetric, asymmetric L1 distance, it is the minimum between D and M, you know? But this is known from previous results. From the key equation I showed you, the very general one, you can prove. So I'm giving you the sketch of the proof only. The start of the proof is this. So the proof of the BCH bound, which is this. For any vector x, write it component-wise in base 3 number system. Okay? So it comes out that any xi is written as the some bi plus bi times b0 times b1 times p plus bm minus 1, p minus 1, right? Well, the bi's now are component of multisets b0, b1, b2, bl minus 1, but now these are multisets over zp, not over zm. So if m is equal to 4, l is 2, so now these guys are binaries, are sets, okay? So then sigma x, you just stick in sigma x in the definition with the roots there, and this is what happens, because this is the property of exponents, right? And you assume that x belongs to x belongs to C, then these things must be equal to this. And then, I mean, it's a long proof, dot, 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 you can prove the theorem. The key points are this lemma there, here, that if you define a lambda, this is talking about the locator polynomial of y is a sigma of the locator, usual locator polynomial, you see, is nothing but the sigma of the support of y. And this is the usual evaluated polynomial of y. You think y has an error pattern in the traditional way, right? Remember, locator polynomial, evaluated polynomial. These are the same thing. Okay? Then you see, look, sigma of y is equal to lambda y times a certain polynomial. And sigma prime also is generated by this word, which is you see, if you do the sigma of this word, you can figure it out. It is equal to a certain polynomial power 4 mod z power 6. So this means that the distance is greater than or equal to 6, and the other distance is the asymmetric L1 distance is greater than or equal to 4. This means that this can correct 3 asymmetric errors. And okay, maybe you might want to add a parity also, which may be interesting too, right? As done. This is a Z4, m is equal to 4, yeah? Oh, and let me notice that the length is 15. see, preparata codes with M15 doesn't work. However, this can correct. For example, when m is equal to 4, this is another code. Oh, so this code is this one. Then there is this other code, m is equal to 8. The codes generated by this one, you compute sigma for this, and you figure it out it is of this form, right? So this means that the lead distance is greater or equal to 12, and asymmetric the L1 distance is greater than or equal to 8. In fact, what I'm telling you is that this can correct 7 asymmetric errors, even measured, but I don't have time to tell you, in the lead distance, lead, which is more than doing it in the L1 distance. Okay? So when D is less than or equal to M, I'm almost finished, don't worry. Then these are asymmetric error correcting codes, the usual one. Okay? The usual one first is first introduced by him. What was Cunningham? 90. When was this? 93. In the Positano law first, remember? Or maybe even before. No, even before. Okay? This can be efficiently encoded and efficiently decoded in a way I told you at the beginning, you see? But even in the Lie metric, not only in the L1 metric, they take log m for any error. Or in the Lie distance, you have to solve this equation. You can do it. It is similar to with the standard Euclidean algorithm, where these are the error patterns. You see. So these are other examples of the roots, and you find out which one are the good sigmas. They have the good sigmas, so that gives you the good metric properties. And okay, these are all examples. Okay, so and let me go leaving these 2 examples here. Thank you for your attention. If there is
Thank you. Any questions?
yes.
So what does you mean for characteristic of a set?
Of a field.
Of field? Characteristic?
It is
No.
the period of the unit.
No.
With the
When
set.
you say characteristic of a code.
Combinatorial characteristic of the code, the distance, how are the codes far apart, you know? It's a combinatorial problem, right? This is a combinatorial characteristic. In terms of the topology, all these distances I said.
Monkeys.
Monkeys, I want to make
Yes,
yes.
question from the monkeys. Another question? Can I ask one?
Yes.
What do you think about Euclidean distance if we map it into Euclidean space?
You know, I don't know, but obviously there are codes which may have a very good distance. Anyway, this is a general result, you know, easy is general, you see. No, there may be very, they may have very good, I mean, what I'm saying, for example, another thing I'm telling you, preparata code, you can describe it in these terms. In fact, just now we figured it out using that the sigma x times sigma of y minus x equal to sigma of x minus y times sigma y formula, general formula. Using that, you can give a new decoding algorithm for preparata codes. You know, because actually we found out it's a sigma code. And not only for preparata codes, but all instances of construction like preparata codes where preparata codes does not work, namely the length 15. But even more powerful codes than preparata codes, Z4 linear codes. You see, those codes usually are known to have a very good distances, you know.
Okay, let's thank the speaker. Session in the afternoon, and it's my pleasure to introduce you Luca Tallini, who is professor at the University of Teramo, Italy. And Luca got his degree in mathematics from the University of Rome La Sapienza in '91, and his master and PhD from Oregon State University in US in '94 and '96 respectively. He's been co-author of over 80 publications, at least up to when this abstract was written, maybe more by now. But he received many awards, 11 awards in Italian and US fellowships. And today he will talk about on linear codes and elementary symmetric polynomials.
Okay, first, organizing committee for inviting me. It was the seed of thinking about the things I'm going to explain to you today. In fact, the point of this is to design, to make algebraic coding theory instead of looking at the usual power sums of a word. Let me readily say that the power sum of a word, the jth power sum of a word is nothing but the expression x1 times a1 power j plus x2 times a2 power j plus ... xn times an power j, where x1, x2, xn are the component of a word, a1, a2, and an ... are field elements, let me say. Okay? Then, I mean, in classical algebraic coding theory, let me say that fundamental is the role, and all the codes have been designed using these power sums. For us, instead, we want to design codes using other symmetric functions, which are the elementary symmetric functions. And in fact, I will show you, at least in an example here, that for the Emari case, this gives new insights of codes. It gives you more information, and you can design actually new codes with this new perspective, with this new framework. In fact, we have been designing new codes, new encoding of all codes, for example, for negacyclic codes of Berlegamps, algebraic decoding procedure, error correcting procedures for high order spectral null codes, and new asymmetric error correcting code. In fact, this theory, with one key equation, let's say, you can design the code, both usual symmetric error correcting code or the new asymmetric error correcting code. Codes suitable for the asymmetric channels. You see, it all is embraced in essentially one equation that I will show you for this case. Anyway, so here, let's fix the point, and later in this talk I'm going to talk about the Emari alphabet, codes over the Emari alphabet, where the Emari alphabet is ZM, I call it. It is composed of the symbol 0, 1 up to m minus 1s. And when m is any natural, and when I make this definition, when m is 0, I mean the natural numbers as a set of symbols for the time being. But usually with natural numbers, you sum, you multiply, right? Okay, so here we give some theorem, efficient design of ZM linear error control codes. You can control codes in various ways. Maybe okay. Which are based, as I said, on the elementary symmetric function of a word, and I will tell you later on what I mean with the elementary symmetric function of a word. Instead of using the power sums, which is what I I will talk of both the Lie matrix between vectors in Zn, and I will define them later on. The application, one word, one sentence on the application. These are codes that are very well suited to control errors when the probability that symbol Y is received, given that symbol X is sent, goes like a constant Cxy, which may depend on X and Y, times epsilon power the absolute value, let's say the distance of X and Y, okay? Where epsilon obviously is a small constant. Maybe you can very well assume that the channel may have a random behavior. So, for example, to model the unidirectional channel also, that you may assume that these constants may be random variable themselves too, okay? But the important thing is that these metrics are very well suited for when, the error goes exponentially with the distance between the received symbol and the sent symbol, okay? And for example, in the repetition channel or sticky channel, somebody calls it, is a channel where you have insertions or deletion of repeated symbols. So maybe you send 3 zeros and you receive 7 zeros. Or in flash memories also, as at the end of Ball's talk yesterday, Andrew was saying, right? And actually, maybe with these distances, more than of the distance that the Ball's talk today, it may be more precise in modulating this behavior of given by this, by this equation for the probability error. Okay, I'm going to talk. Excuse me. Yeah, no. I'm going to talk about a general class of GOPA, BCH-like ZM linear codes, and given a field of characteristic P. And M, I am going to focus myself on when M is a power of a prime number, where P is a characteristic of a field, so we have a field, prime number, and M is a power of the prime number, of the characteristic of the field. For the BCH-like ZM linear codes, we prove a BCH-like bound on the distance, but which distance? With respect. Okay. Also, for example, when P is equal to 3, 5 is a prime, we present a class of T asymmetric error correcting codes, namely codes that can correct T asymmetric error, or for those who know, the minimum asymmetric distance is greater than or equal to T plus 1. A couple of the ZM linear, which are cyclic code, are sigma codes in the sense they are designed with these elementary symmetric function, which I call them sigma, so this is why I call these codes sigma codes. CT plus 1, whose alphabet size is MN, is P power L. So P is 2, L is 2, is Z4. Symbol are 0, 1, 2, and 3. The length is the cardinality of the field minus 1. So, for example, GF 16, M is 15. The error correcting capability is T less than M. So if M is equal to 4, then this corrects, I can give you a design to correct 1, 2, and 3 errors, right? And the redundancy is essentially T times the logarithm base M of K, which is quite good. Namely, the logarithm of the size of the length of the codes. Each of these is, I have to spend to correct one more error, right? In the Amari case, usually, in the usual case, you need 2 times, usually, with the PCH codes. So these are also easy to encode because are ZM linear codes, and easy to decode with the general formula, the one that I mentioned before, as is a general key equation, and because these are sigma codes, and you will see what the sigma code will mean now. For example, let's say M is equal to 4, I am giving you the code generated by all linear combination of this word and its cyclist shift secret codes, right? So this generates a code whose length is 15, the number of information digits is 9, so the redundancy is 6, and it corrects 3 asymmetric errors, and this is in fact a sigma code that I still have to define, but I already defined in this example. I'm telling you, you take 3, right? And index and support of X is 1, 0, 1, 1. Is it clear? I go forward. So let Gm be naturally ordered at 0 mean less than or equal to 1 and so on. And the natural subtraction is the minimum if X is greater than Y is X minus Y, where minus is the usual minus. Otherwise it's 0. Then the component-wise natural subtraction is this. So I think you understood me, but anyway, here are 2 examples. So X is 0, 1, 4, 2, and the other one is 4, 3, 2, 1. So X minus Y is 0, 0, 2, 2 minus Y is 1. Vice versa, Y minus X is 4, 3 minus 1 is 2, and then 0, 0 because those are less, okay? Also, I need to introduce the Lie absolute value, which is defined as it depends on M. Be careful. If M changes, the Lie absolute value changes, and it is the minimum between X of M minus X, namely on the if you put the symbols on a graph, it's a cycle, on a cycle graph, then it is the minimum distance induced in this graph, right? Instead of being a linear graph. So the Lie vector is, I take now the of X, I take component-wise, I apply gamma to any element of the vector. So it's nothing but this. For example, gamma 5, 1, 3, 2, 4, 0 is 1. 3, the absolute value is 2, so it's 2. The absolute value is 2 is 2. The absolute value of 4 is 1, and then 0. So the Lie weight is, you add all the elements, is the cardinality, let me say, of the gamma X. So the Amari weight, sorry. The L1 weight of X is the cardinality of the multiset. The Lie weight, Amari weight is the cardinality of this guy, okay? And the Hamilton weight is nothing but the cardinality of the index set of the word, 0, 1, 4, 2, and okay? Oh, and note that there is this relationship between these weights. Okay, now the symmetric L1 distance which is nothing but the L1 distance the mathematician knows, but in these terms can be defined also as, sometimes this is known